I want to introduce our first speaker this morning, Andrew Lo. Andy is a professor of finance at MIT and is also the director of the Laboratory for Financial Engineering at MIT. In introducing Andy, you'll see in his bio is an incredibly broad background. As a financial economist, and he started off as a sort of a traditional financial scholar, studying methodology of financial research, how financial markets behave in a statistical sense, very highly technical research. He has moved to derivatives, trading, the study of hedge fund strategies, risk and return, and most recently he's become interested in sort of the evolutionary and neurobiological foundations of finance. So in a way, Andy, as we talked about last night at dinner, he's sort of come sort of the full circle from being sort of traditionally trained financial economist and now sort of entered sort of behavioral finance, but in a way that is very different from maybe sort of the traditional path that people have taken. So the title of his talk is going to be "Can Financial Engineering Cure Cancer?" It's sort of a, one of these, great questions that you want to know the answer to after you just read the title of the talk. And he told me that he first became interested in economics when he was an undergraduate at Yale. So in a sense, it's my pleasure to just welcome him back today here on the podium. Andy.
I want to start by thanking Geert for that very generous introduction and welcome, and to thank Will Getzman and Geert for organizing this terrific conference, and to thank all of you for coming. It's a little daunting to be speaking at a conference called The Future of Finance, and there are a number of very impressive academics and practitioners involved, so it's a little intimidating. But one of the nice things about the topic that I'm going to talk about is that I have absolutely no expertise in this, and I can say that up front, so the expectations should be pretty low. My interest in healthcare finance really came about for personal reasons. I don't have any biomedical background. I'm not even a healthcare economist. As Geert mentioned, most of my research has been in traditional finance. But a few years ago, a number of friends and a family member were diagnosed with cancers of various different types. And so I started learning a little bit more about their situation, trying to help them out as best I could. And as an economist, I couldn't help but try to understand a little bit more about the economics of cancer therapeutics. And through that process of discovery, I came across something that I really couldn't understand, a contradiction, a conundrum in the industry that I wanted to share with you as motivation for what I've been working on ever since. And the conundrum has to do with the following observations that I made. Over the course of the last 10 or 15 years, scientists and clinicians have made tremendous progress in dealing with all sorts of diseases, including cancer. For example, in 2001, Gleevec, a new drug, the first of its kind, was launched by Novartis to treat leukemia. And unlike many drugs beforehand, Gleevec was designed from the ground up through the understanding of the molecular basis of leukemia, one of these designer drugs, using high-throughput screening methods and molecular biology. And for many patients, it worked like a charm, turning a death sentence into a chronic, manageable condition. 2004, Avastin, another leukemia drug, was approved. In 2006, a kidney cancer drug, Sutent, was approved, all using these incredible methods for developing these therapeutics. And in 2008, after the human genome was sequenced in 2008, scientists turned to sequencing cancer genomes, and Washington University's Genome Institute was the first to sequence leukemia genome. But what really struck me was what happened in 2012. In 2012, a fellow by the name of Dr. Lucas Wortman, a researcher at WashU's Genome Institute, developed a second recurrence of a particularly nasty form of leukemia called acute lymphoblastic leukemia. This is a kind of leukemia that kills in a matter of weeks and months, not years. Now, this was a second recurrence for him. He had gotten it when he was a grad student. It had come back after he had graduated, and now as a researcher, he got it again. The survival rate for a first-time recurrence of acute lymphoblastic leukemia in adults is about 5% over the course of 5 years. We don't actually have statistics for what the probability of survival for a second recurrence is because there are so few people that have actually made it that far. And so when he got the second recurrence, he started putting his affairs in order and saying goodbye to his friends and family. He knew he was going to die. Well, it turns out that his friends were researchers at WashU's Genome Institute, and they decided to put out a 24/7, no-holds-barred, all-hands-on-deck effort to try to save their friend. So they did what they do best. They sequenced his genome. They sequenced his leukemia cells' DNA. They even went so far as to sequence the leukemia cells' RNA, which is not typically something you would do in dealing with these kinds of diseases. But in doing so, they discovered a gene that was overexpressed. And using high-throughput screening methods, they identified a chemical compound that suppressed that particular gene. Turned out that that chemical compound was Sutent, this kidney cancer drug. So they gave it to him. Now, Sutent is not approved. At the time, it was not approved for treating leukemia, but they gave it to him anyway. Within days, he felt better. Within weeks, he was back at work. And several years later, he's doing just fine. For all intents and purposes, he's been cured of this terrible affliction. Now, oncologists will never use the word cure because they know, as well as many of you do, that cancer can come back with a vengeance because it mutates. But as far as we know, it seems like he's pretty much back to normal. And so he made the front page of the science section in the New York Times in 2012 as a poster child for the new medicine, so-called targeted therapy, personalized medicine. But what's amazing about the story is that in the same year, David Aponte, an NBC Studios technician, also came down with acute lymphoblastic leukemia. And he was also treated, but he was treated with a completely different therapy, with immunotherapy. Scientists and clinicians took T cells out of his body, trained it to attack the leukemia cells, put it back in, and months later, they can no longer detect any leukemia cells in his body. So we are in a new era of medicine. We're at an inflection point. So what's the paradox? Well, the paradox is that at the point at which we are at this inflection point, money is being diverted from these activities. Funding is actually declining for early stage translational medical research, which seems crazy as far as I could tell, because we're on the brink of making some really transformational discoveries, and it seems like it's only a matter of money. So why are we pulling money out? Well, we know that NIH has declined in their funding for a variety of political reasons that may not make a lot of sense. But even in the private sector, as well as the biotech market is doing, the biotech bubble that seems to be on the verge of bursting is really funding companies that were started 7 to 10 years ago. The number of new companies that are being started is actually going down. In fact, if you look at the number of biotech VCs, in 2008, there were 201 of them in this country, and by 2013, that number's gone down to 137. And over the course of the last 10 years, the number of Series A financings, early stage startups in biotech has really gone down quite a bit. And it looks like it may be on the upswing, but we don't know. It seems too early to say. So the question is why? Why is it the case that we've got all these amazing breakthroughs and more to come, but we're actually taking money and deploying it in other fashions, in other ways? So as an economist, I can't help it. To someone with a hammer, everything looks like a nail. I'm looking for an explanation that has to do with incentives. And the narrative that my co-authors and I have come to is that the reason that money is hard to come by in this idea-rich field is because of increasing risk and uncertainty. Risk being the randomness that you can quantify, and uncertainty being the unknown unknowns, the randomness that you can't quantify. Both are increasing. So let me give you a bit of an illustration, because I couldn't understand it at the time, so I tried to develop some kind of simple narrative that would make sense to me. Well, here's one narrative, and it has to do with something called Eroom's law. This came out of an article from a medical journal a few years ago. And I don't know if any of you have heard of Professor Eroom. Anybody know who Professor Eroom is? Well, there actually is no Professor Eroom. Eroom is Moore spelled backwards. It's the opposite of Moore's law. Moore's law is the law that says that we're getting more and more efficient in designing these semiconductor chips. It turns out that in the medical industry, the reverse seems to be happening. This is a graph, this downward sloping graph, is a graph of the number of new drugs approved divided by the amount of R&D dollars spent. And you can see that it's been going down for the last 6 decades. And by the way, this chart is on a logarithmic scale. So we are becoming exponentially worse and worse in developing new drugs, at least from an economic perspective. Why is that? Well, it has to do with complexity. Normally, at least in finance, you think about when you get smarter, things get easier. The risk goes down once you learn more and more about an investment. But in biomedicine, I discovered that the smarter we get, sometimes the more difficult things are, the more challenging drug development becomes. So here's an example. Combination therapies. You've all heard of the ability for different drugs that aren't particularly effective by themselves to work wonders when you put them in combination, when you take them together. The best example, of course, is HIV. AIDS was a terrible affliction that killed millions of people around the world. One of my beloved high school English teachers, Ted Rifkin from Bronx Science, he died of AIDS in the 1990s. And we now know that in combination, a number of antiretroviral drugs can actually turn AIDS into a chronic condition that can be easily managed. In fact, one of the antiretroviral drugs that was developed right here by a professor of pharmacology, Young-Chi Chang, I believe. So combination therapies can be amazing. So how do we go about discovering them? Well, there are currently 2,800 approved drugs out there. So let's suppose that we take these drugs 2 at a time in order to see whether or not we can find a good combination for a particular disease. How many different possibilities are there? Well, those of you who've taken introductory statistics, you know the binomial formula. 2,800 choose 2 happens to be 3,918,500 pairs, each one of which requires a separate clinical trial before it could become standard of care. And if you take them 3 at a time, we're talking about 3.6 billion triplets. And by the way, the AIDS antiretroviral cocktail, that's 5 drugs, 5. It is literally impossible to go through all the combination of different drugs, dosage regimens, biomarkers, and other challenges through brute force. It's becoming incredibly complicated to develop drugs. And investors respond to that increase in complexity. So it has to do, in my view, from an economic perspective, with risk and reward. So let me turn from drug development to finance and ask all of you to think about investing in 4 different possible investments, okay? So I'm going to show you the growth of a $1 investment over the course of a series of years. And your choice is to pick one of these 4, and only one, to invest your entire net worth. So here are the 4. I'm not going to tell you what they are until afterwards. So you're really just going to focus on the performance of these things over the course of the last few years. So the first investment is a relatively boring investment. You start off with $1, you end up with $2 over a period of years, not a lot of up and down. The second investment, the red line, ends up at about $4.50, but it's quite a bit more volatile. Third investment is even more volatile than that. You end up at about $8, but through lots of ups and downs. And the last investment that I want you to consider is this black line, which ends up at about $5, but in a somewhat less volatile fashion. If you had to pick one of these four investments, which would you pick? How many people would pick the green line? Show of hands. Wow, nobody? Okay, how about the red line? How many people would pick the red line? Wow, no takers. Okay, blue line? Okay, these are the hedge fund managers, okay? And how about the black line? Yeah, most everybody else. Well, the black line is the most popular, not surprisingly, because it's got the right combination of reasonable return and relatively low risk. Let me tell you what these four investments are. This is from a period from 1990 to 2008, and the green line is US Treasury bills, not very exciting, and certainly not something you can retire on. The red line is the S&P 500, which none of you picked, which I was quite surprised by. The blue line is the single stock Pfizer, which is very volatile and has gone through ups and downs. And finally, the line that most of you picked, the most popular investment, is the return on Fairfield Century, which is the feeder fund for the Madoff Ponzi scheme. Now you know how that Ponzi scheme got so big. We all like return, and we all don't like risk. As the risk increases, we say, no thank you. And as the return starts to look better and better, we start pouring money in. So let me give you a simple narrative of what, from an economist's perspective, is going on in the biopharma industry. These are the back of the envelope numbers that I came up with for what it costs to develop a single anti-cancer compound. $200 million investment, 10-year horizon to go through these clinical trials, and the probability of success for developing a truly effective anti-cancer compound historically is 5%. 5% probability of success, 95% probability of failure. In the unlikely event that you are successful in developing an anti-cancer compound, you get $2 billion a year in earnings for about a 10-year period, which is how much patent life you have left after you've gotten the drug approved. So from years 11 to 20, it's about $2 billion a year. And so at a cost of capital of about 10%, which is what the pharma industry uses, that amortizes to a payday in year 10 of about $12.3 billion for a $200 million investment up front with 5% probability, a 95% probability of nothing, which means that you can get either a compound annual rate of return of 51% over the 10-year period, or you'll get minus 100% with 95% probability. For those of you who are taking quantitative finance, let me translate this in terms that you will understand. This is a 12% expected rate of return and a 423.5% standard deviation. How many of you would like to invest in this? Show of hands. Yeah, one or two people. This is way too risky for most of us. And that's one of the reasons why money is leaving the space. It's a lot more compelling to invest your money in an app company, which costs maybe a few $100,000, and in 2 or 3 years' time, it gets bought by Facebook for $19 billion versus putting your money into something like this. But what if we, instead of investing in one of them, what if we invested in 150 of them? Financial engineering can actually help us reduce this risk. Now, you might ask, how are we going to be able to do that? If you want 150 of these, it's going to cost you $200 million times 150, or $30 billion. Where on earth are you going to get $30 billion? Well, as an economist, I have a very straightforward answer. Assume we have $30 billion. Now, I'll show you in a minute why I'm going to assume that. I'm going to argue that with 150 programs that are statistically independent, and I'll come back to that assumption later, With a 5% probability of success, if you put 150 of these together into a portfolio, it turns out that diversification, multiple shots on goal, to use a hockey term, will actually make this return a lot more attractive when it comes to reducing the risk. So here's how. With 150 trials, each with a 5% probability of success, and they're statistically independent, the probability of 2 or more successes you can calculate as a simple binomial probability. It turns out that it's 99.59%. Let me repeat that. If you take 150 shots on goal, each with only a 5% probability of success, the probability you'll have at least 2 successes is 99.59%. If you have at least 2 successes, that means you have at least 2 times $12.3 billion in year 10. And if you discount that at the AA rate of 2.75%, what you get is that by issuing cancer bonds on 150 projects, you can raise $18.7 billion through high quality debt today. Now, how do I know that it's AA rated? Well, what's the probability of default? It's the probability of not being able to earn $24.6 billion in revenue. And what's that probability? Well, it's 1 minus 99.59%, which is 41 basis points, which puts you right in that AA rating according to Moody's and S&P. And if you allow me to use all of the tricks of the financial trade, things like securitization, credit default swaps, I can do even better. Now, some of you are chuckling a bit nervously. Is this really a good idea to be using the same instruments that created the financial crisis? And I have to tell you that it was really the financial crisis that got me to start thinking along these lines. It's not that these tools didn't work, which gave us the financial crisis. It's because these tools, they worked way too well. These are power tools in being able to gather assets and direct them in various different ways. And one of the ways that we directed them was US residential real estate, which is what created this incredible run-up in real estate prices and the ultimate decline. What if we could take that same force and direct it towards things like curing cancer? Do you think we could have an impact? Now, the way that this works, as you well know, is that diversification relies on correlation. The fact that assets may be correlated will actually reduce the probability of that success rate. So here's a graph of the probability of at least K successes or more with 150 shots on goal, each with a 5% probability, and assuming that they're uncorrelated. That curve at K equal to 2 is 99.59%, as I said. If I now assume that the correlations among these different projects are not 0, but 10%, the probability of at least 2 hits goes down to 96%. And if I assume the correlation is 40%, the probability goes down to 70%. And if I assume that the correlation among these projects is 80%, then there's only a 30% chance that you're going to have at least 2 hits. At 30%, you can't issue debt. It's way too risky. The probability of default is so high, nobody is going to even want to rate your debt, never mind buy it. So correlation is the key, not surprisingly. When I told this to one of my pharma contacts, he said, you know, this is exactly what he's been telling his colleagues for years, but his analogy is not with these probability curves, it's with his daughter's 3rd grade soccer team. I said, what do you mean? And he said, well, I coach my 3rd grade daughter's soccer team, and when I first started, I realized I had a challenge. And the challenge is that when you're coaching kids soccer, you've got to tell the kids to spread out. They all crowd around the ball. And when you compare this to World Cup soccer, you see the difference. Pharma companies, according to this colleague, are all crowding around the ball. And his argument is you ought to spread out. And when he saw the financial calculations, he said, this makes a lot of sense. Now, there are good reasons why you might want to crowd around for a scientific discovery, but at the same time, for reducing risk, you've got to diversify. So do we really need 30 billion? Well, the short answer is as any economist would tell you, it depends. It depends on the underlying parameters, the probability of success, the correlation among the failures, the cost, the benefits, and so on. And so over the course of the last few years, I've collaborated with a number of people in the biopharma industry to actually simulate what a mega fund would be in terms of its risk and reward using various different parameters. And in some cases, we find that, in particular for cancer, you do need multiple billions of dollars because that's what it costs to develop a cancer drug. But for other kinds of afflictions, actually, you don't need nearly as much. For example, in a recent paper that we published just earlier this year, in collaboration with some researchers at the National Institutes of Health, we actually looked at their existing portfolio of drugs for dealing with rare diseases, diseases that affect 200,000 patients or less, according to the Orphan Drug Act of 1983. That's what a rare disease is. And when it comes to rare diseases, there are all sorts of parameters that make these kinds of targets a lot more amenable to smaller funds. So with just a couple of $100 million, you can actually put a very attractive risk-reward ratio on the table for investors. In this simulation, using actual data from NIH, they've got 28 rare disease projects that they're developing. If you were to assume that that was a private sector effort and you used market valuations for what they're doing, we estimated a 21.6% rate of return for investors for their rare diseases portfolio. Now, they're actually not doing this commercially, but there's legislation that's pending in a couple of weeks that will actually, if passed, give them the authorization to engage in a public-private partnership. So these methods can actually be used in practice. And it's because the statistics actually justify it. So here are the same probability curves, but instead of 150 projects, only 20 projects. But here, instead of changing the correlation, what I'm going to do is vary the probability of success, assuming that they're all uncorrelated. And the reason that that's a decent assumption in this case is that typically rare diseases are caused by genetic mutations. And by definition, genetic mutations are actually random and uncorrelated across afflictions. Turns out that with a 5% success rate and 20 projects, the probability of at least 2 hits is pretty small. It's about 25%. Nobody's going to want to finance this. But as you increase the probability of success from 5% to 10 to 15 to 20%, the probability of 2 hits or more goes up significantly. And some scientists tell me that the probability of developing a successful drug for rare genetic disorders can be as high as 80%, in which case the financing becomes very, very attractive for investors. Now, can you earn a decent rate of return on investment for rare diseases? Well, here's some examples. All of these drugs were approved as rare disease therapeutics, which is kind of amazing because one of the drugs happens to be a breast cancer drug called Herceptin. Breast cancer is not a rare disease. It affects 230,000 women every year. 30,000 women die of it each year. But it turns out that thanks to the magic of molecular biomarkers, we can now stratify the patient population into smaller subsamples, each of which can be considered a rare disease. By dividing and conquering, we can actually develop therapeutics and be able to get them out in a much more cost-effective manner, but more importantly, we can actually finance it using these kinds of techniques. Now, you might ask, isn't pharma already doing this? Why does finance have to play a role? The answer is, it used to do this. Big pharma used to develop these drugs, but more and more lately, they've been engaged in other kinds of activities. So here's an example. Pfizer, one of the largest drug manufacturers in the world, Pfizer has on its balance sheets $36 billion of cash, of which $31.5 billion is financed by long-term debt. So Pfizer actually looks like one of these $30 billion mega funds. But Pfizer is not using its $30 billion to develop early-stage translational medical R&D. What they're doing is what their shareholders want them to be doing, which is focusing on acquisitions that will improve their multiple. So basically, they're going out and trying to find portfolios of drugs after the risk has been taken out through that R&D development effort. And why are they doing it? Well, because we as shareholders are telling them to do that. In 2010, Morgan Stanley published a controversial report about how the pharma industry needs to reinvent itself. And the title of this research report was called Exit Research and Create Value. And in the report, the author writes, the solution, our economic value added analysis supports replacing research with search. On current market economics, we estimate that $1 invested in in-licensed compounds will, on average, deliver 3 times as much value as $1 invested in in-house research. And pharma listened. Over the course of the period from 2008 to 2013, pharma cut nearly 150,000 jobs, most of which was in R&D. Because R&D is getting harder and harder. A lot of it is happening in academic medical centers, universities, hospitals, as opposed to pharma companies, because the complexity of medical discovery is increasing. It's becoming much harder for any one company to be able to do this. Here's an example that is close to home. Sanofi, earlier this year, committed $845 million to a biotech company in Cambridge to develop a new therapy. That same day that they announced this $845 million partnership with this fledgling biotech company, they also announced they were laying off 100 of their full-time R&D staff. And so new business models are emerging, not a pharma company, not a biotech VC, not a mutual fund, but elements of all of these businesses, because the drug development process contains different levels of risk at different phases, and it means that different kinds of financial structures are going to be appropriate. The closest thing to what my co-authors and I have been focusing on for this Megafund proposal is really the drug royalty investment company, companies like Royalty Pharma, which basically invest in a variety of different projects, pool the risks for their investors, and are able to pump billions of dollars into the industry. So in the last few minutes, since I'm running out of time, I would like to propose that we can actually structure a megafund with not too much difficulty given the technology that already exists in the industry. So can the financial industry cure cancer? Let me ask you to use your imaginations. And I'll describe to you an investment, and I'll ask you whether or not you would be willing to invest in this fund. Suppose we create a $30 billion cure for cancer fund. I know it sounds ambitious, and oncologists don't want to use the word cure, but let's focus on really trying to do something transformational. And let's suppose we created a portfolio with projects from a variety of different sources. Some of the best universities in the world, MIT, Yale, and some lesser universities. Some other academic medical centers, some research centers, some hospitals, and some pharma companies. So we have a portfolio of 150 of these projects. And let's suppose that we created an amazing advisory board of experts on the biomedical side, as well as on the business side. Experts that have deep scientific and business understanding of the biopharma landscape. And let's imagine that a very large, reputable fund family were to offer a vehicle to both retail investors as well as institutional investors. If such a fund existed, would you be willing to put $3,000 of your 401k in this fund as a one-time investment? Now, before you answer, I'm going to ask you to raise your hands. Before you answer, I want to close with one final story that may change your mind. It changed mine about the feasibility of this approach. I want to tell you about this man. This is Harvey Lodish, a professor of cell biology at MIT, a colleague of mine, and a faculty member at the Whitehead Institute. I've got to tell you that once I heard about Harvey's story, I wanted to be Harvey Lodish. And let me explain why. So Harvey was approached in 1986 by a venture capitalist to develop a therapy for a terrible but rare affliction called Gaucher's disease, Gaucher syndrome. And Harvey was not a drug developer, but he was a cell biologist that was particularly expert in cell membrane properties, and that was key to being able to develop this affliction, which affected only 15,000 patients at the time, but for those patients, this was a death sentence, and with this drug, they could actually live a normal life. So Harvey worked on it, and in 1992, the drug was approved. They started a company, he got shares in it, and everything worked out quite well for all parties concerned. You may have heard of the company. It's called Genzyme. But that's not why I want to be Harvey Lodish. The reason I want to be Harvey Lodish is that in 2002, a decade after the drug was approved, Harvey's daughter became pregnant with her first child, Harvey and his wife's first grandson. And in utero, the baby was diagnosed with Gaucher's syndrome. Now, having the genetic marker doesn't mean you'll get the full-blown disease. You have to wait till you reach puberty to tell. And Harvey's grandson turned 10 in 2012, and he did develop Gaucher's disease. But he's just fine, thank you very much, because of Grandpa's drug, a drug that was developed 2 decades before Harvey had any inkling that his grandson would need it. That's why I want to be Harvey Lodish. Now, I can't be Harvey Lodish because I don't have an MD or a PhD in molecular biology. But I can be Harvey Lodish if I invest in a fund that develops a cure for my as yet unborn grandchildren. So let me ask you now, how many of you would be willing to invest in this fund? Well, I only needed 8% of you to say yes, because with 130 million households, 8%, $3,000, I've got more than $30 billion. We can cure cancer with finance, but we need the right structure. And I'm so grateful for the opportunity to talk here because the people in this audience, you can do this. The students in the audience, you are the future of the financial industry. And if you take these ideas and implement them and realize that finance at the proper scale, you can do well by doing good, that finance doesn't have to be a zero-sum game. If you take that and apply it, we will cure cancer. Thank you. Yes.
Andy, my name is Mark Barron. I'm a classicist at the Yale College, and I appreciate the microphone. I want to applaud you for your presentation, and particularly it's close to my heart and some folks that I represent on the, I'm a board member for the National Foundation of Cancer Research based in Bethesda. You may know the organization. We actually have sponsored Dr. Tommy Chang here at Yale, in addition to Dr. Dvorak at the Deaconess. Mm-hmm. So we support scientists at several institutions in the United States, including groups abroad. And we are, in fact, been trying to do what you so eloquently described here from a financial point of view. And I would just encourage people here in the audience to follow Andy's inspirational comments. We provide adventure funding for scientists in basic cancer research, and have been doing that for 30 years. And so, again, I thank you for your presentation and look forward to speaking to you afterwards.
Thank you, I really appreciate that. And you bring up a very important point, which is that funding for basic science is absolutely critical. Most people think that when they contribute to an effort, what they really want to do is develop drugs. The problem is that you don't get those great drugs until you develop the basic scientific understanding of how the disease works. And that's really where a lot of the benefit of early stage translational medicine comes. It's really from starting with the basic science. And unfortunately, foundations, patient advocacy groups, they are now becoming more and more important because the federal government is actually cutting back on funding for basic science. So thank you for your support for this research. Yes.
Hi, I'm David Tedden, Yale College, partner with FF Venture Capital. So I am all in favor of institutionally de-risking early stage risky investments. The traditional mechanism, as you know, for that is VC funds.
Right.
So it would be great if you could clarify the distinction between your megafund model and the traditional VC fund model. Debt is an obvious difference, so it'd be great if you could expand on that, and scale is the other. But as you know, in the VC industry, people typically refer to it as a non-scalable asset class.
Right.
Because in practice, large VC funds tend to break apart. So can you comment on that?
Sure. So first of all, thank you for bringing that up. I should have brought it up myself. The venture capital model, many people have argued, is broken in biomedicine. VCs are not broken. A lot of the expertise in deploying these kinds of funds rely on VC expertise. But venture capitalists are just as frustrated as the rest of us because the business structure of a venture capital fund turns out to be not well suited for biomedical discovery, mainly because we're talking about very long-term effort, very risky, low probability of success, highly complex. That's not ideally suited for a fund that may have a 5 to 7 year horizon where you have to have milestone payments along the way and potentially inpatient investors. So the VCs, I've spoken to a number of biotech VCs that are frustrated that their investors, their limited partners, have become less patient, or rather more enthralled with other kinds of investments that are so-called lower hanging fruit. So what we've seemed to come to is the fact that we need a new business model where venture capitalists can actually deploy capital over longer horizons. One way is to use debt, long-term debt. The second is to get much larger scale. To the question of whether or not you can get scale, I think that there are differing opinions. I'm not an expert on it, so I'm not qualified to say. But from talking with a number of biomedical experts, they tell me that for certain fields, particularly oncology, now scale is possible. It wasn't possible 10 or 15 years ago when we didn't know enough about cancer biology, but a lot's happened. By the way, it's only been in the last 12 years that we've actually sequenced the human genome. Think about that. 2003 was when we completed the sequencing of the human genome, and now virtually every cancer therapy begins with some kind of a genetic screen. So the argument is that de-risking a portfolio would not have been possible 10 or 20 years ago, but today it is in much larger scale, but it's not going to be possible for all areas. So one example where it's not possible, in my view, is Alzheimer's disease. We don't actually have enough targets there because the basic science in Alzheimer's is not nearly as well developed in cancer. Yes, down. Oh, sorry, up there. And then
Thank
down.
you. I'm Susan Curley, SOM class of 1978. And first of all, I want to commend you. It's so great to hear finance kind of coupled with the public good. My question comes on the back end around some of the public debate about healthcare costs, about costs of drugs, about allocation of drugs, globalization, if you will. So I'm just wondering how those considerations factor into your planning.
I mean, they factor both directly and indirectly. Certainly directly in the sense that when we run our simulations, one of the parameters is what are your revenues going to be if you get a cancer drug approval, and that depends on what you get in terms of reimbursement. So it's a very important component. And by the way, all of our simulations, we actually post our software online with an open source license. Anybody can take it, run it, change the parameters, steal our software, give it away, do whatever you want to use it to be able to see whether or not these results will hold up under various different scenarios. So the question, though, that I think you're getting at is it sustainable? Is the crazy prices of some of these drugs sustainable? And I'm not a healthcare economist, so I can't answer that. I've actually asked a number of my colleagues who are healthcare economists. They tell me that from a political perspective, there is absolutely no desire on the part of politicians to push back at this point on pricing. However, if we keep having these escalating prices, there is going to be pushback, and we've already seen it happening with Sovaldi, hepatitis C, with certain kind of cancer drugs. There's the beginnings of concern. But I have a somewhat different perspective. My perspective is that there are a number of issues, a number of challenges with the healthcare system that need to be addressed, including the fact that we don't have a single payer system, we don't necessarily reimburse based on efficacy, and so on. All of those challenges are not going to be dealt with until we are pushed to dealing with it, until push comes to shove. How are we going to get push to come to shove? My view is the way we do that is by trying to break the system. In other words, let's develop so many incredible therapies and charge outrageous prices to the point where the politicians say, we can't keep doing this anymore. We're going to have to fix the system once and for all. We're not going to be able to get there until we push the system to that limit. But let me give you a second sobering perspective that took me a little bit of time to come to, which is, can we really afford all of this new medical care? Because right now we're spending anywhere, depending on how you count, between 8 to 15% of GDP on healthcare in this country. Is that sustainable? Well, let me ask you from a personal perspective, is it sustainable for each of you to spend 8 to 15% of your net worth on healthcare? Well, let me ask you to imagine something. Imagine that one of your family members, a child, your mother, father, is diagnosed with a terrible terminal illness, God forbid. But I can cure it for you. We can develop personalized therapies, just like for Dr. Lucas Wortman. I can develop a targeted therapy for your loved one, but it's going to cost $1 million. Would you do it? Now, $1 million, for some of you may not be a lot of money in this audience, but for many of us, it is a lot of money. It's many, many years, our annual income. Would you do it? I can't imagine a single person in this room that would say, no, no thanks. We can let grandma die. We can let our child die, no problem. We will all spend the money. And I'm not saying that this is a good thing or a bad thing, it's just a human thing. We will spend tremendous amounts of resources if there exists life-saving therapies. And over the course of the next decade, there are going to be more and more life-saving therapies. That is both a wonderful windfall, but it's also a huge economic challenge that we have to deal with. Yes.
Last question.
Oh. Yes, here. Sorry.
Is there applicability of this model, Kevin Murphy, and is there applicability of this model in other aspects of public policy, taking a negative externality and trying to bring down the prison population or traffic accidents or pollution? Is it possible in other venues?
So, in my view, definitely, but you have to pick and choose. And let me tell you what the components are. So the reason that we focused on cancer initially is because we know that regardless of whether or not our parameters are correct or slightly off, if you develop 1 or 2 successful cancer drugs, that will more than pay for all of the failures that you might have to suffer. It's because we know what cancer drugs command. The same argument does not apply if, for example, you were targeting, I don't know, athlete's foot. With $30 billion, I'm pretty sure you can cure athlete's foot, but you're not going to earn a decent rate of return on it. So the question is, what kind of challenges out there are ones where society is desperate for and will pay for a solution? Climate change, energy, all sorts of challenges that we face in society can command tremendously handsome returns, but we have to figure out what the appropriate structure is. This won't work for everything, but for some of society's biggest challenges, it will. And with your help, we will be able to do that. Thank you.